What makes you believe something is true? The evidence given to support it? The way it's presented to you? Or just who says it? Or the evidence of your own eyes? Throughout our lives, we build up a bank of so-called common knowledge, of things we were told when we were younger, or things that we see in the media or in pop culture that we just take to be true. But if you step back and really look at these assumptions, we often find that our understanding of the world around us is built on very shaky foundations.
Hiya, Dylan here. Welcome to the second video of the mini-series Sci-fi or Fact. We'll be taking a look at some of the common tropes of pop culture and sci-fi and seeing how well they measure up to reality. This video we'll be looking at the depiction of invisibility. Invisibility is depicted in many forms of pop culture, from Harry Potter and his invisibility cloak, to James Bond's car in To Die Another Day, or even things like cloaking devices on ships and a dearth of sci-fi such as Star Trek and Star Wars. But before we can start looking at how realistic invisibility actually is, and if you can actually make something invisible, we first have to understand how we see things in the first place. That means we need to take a look at light, and how light behaves when it hits an object. So as I'm sure you already know, from every time you turn off your lights before going to bed, we rely on light to see. Our sight works by light from a light source striking an object and then travelling into our eyes, which our brain then interprets as an image. This means the way we see, or maybe don't see, an object is determined by how light behaves and interacts with that object when it hits it, how our eyes then take in that light, and how our brain then interprets the light that our eyes take in. So understanding the way light can behave when it hits an object is essential for understanding how we see things, or how we can make something unseen or invisible. One thing to note before we start breaking down the behaviour of light in detail: our brains work on the assumption that light always travels in straight lines in our ever-changing direction, and we interpret all light in this way. This idea will come back later, so keep it in mind. So when light strikes an object, it can behave in three different ways. It can reflect, it can refract, or it can be absorbed by the object. The main two which we're going to focus on in this video are reflection and refraction. So let's start off looking at reflection. To help us look at the behaviour of light, we're going to be using some diagrams like this one here, which are called ray diagrams. On ray diagrams, light is drawn by straight lines with an arrow on them to show which direction the light is going in. The other main feature of ray diagrams is a dashed line, which is at 90 degrees, or perpendicular to use the proper word, to a surface that light hits. This line is called the normal. Reflection is when light travels towards a surface, strikes it, and then bounces off the surface. One of the important things to note about reflection is that the angle at which the light comes in towards and hits the surface, called the angle of incidence, is the same as the angle with which it leaves the surface, called the angle of reflection. Let's use what we now know about reflection and about how our brain processes light that reaches our eyes to understand what we actually see when we look in the mirror. So as you look in the mirror and light bounces off the top of your head, hits the mirror, and then goes into your eyes, the light actually moves like this. However, remember that our brain always imagines light to be moving in a straight line and to have always been moving in that direction. So our brain interprets this light, which has bounced off our head, reflected off the mirror and then gone into our eyes, to actually be originating from a source behind the mirror. Likewise, for when light bounces off our foot, then reflects off the mirror and into our eyes, our brain imagines that this light also has always been travelling in a straight line and therefore must originate from behind the mirror. This is why when we look in the mirror, the image we see of ourselves looks as if it's behind the mirror on the other side of it. Refraction is another behaviour of light, which our brains sometimes struggle to understand. Refraction is when light bends as it speeds up or slows down when it enters a new material. If light speeds up as it enters a new material, it will bend away from the normal line, and if it slows down entering a new material, it will bend towards the normal line. A number is given to every material to define how fast light moves in it. This number is called the refractive index. A vacuum, which is the complete absence of any matter or material, is the medium light moves fastest in, and it's given a refractive index of 1. The refractive index of a material gets bigger the slower light moves in it. So a material with a refractive index of 2 has light moving at half the speed inside of it of the vacuum with a refractive index of 1. And similarly, if an object has a refractive index of 3, then light moves at a third of the speed that it would in a vacuum. So for some common materials, water has a refractive index of roughly 1.3 and glass roughly 1.5. Let's use what we now know about refraction to help solve a classic problem which I'm sure cavemen found very frustrating. Say you're trying to fish or hunt a fish in water. Light travelling from the fish travels in a straight line whilst in the water until it reaches the boundary between the water and the air. As air has a lower refractive index than water, the light accelerates as it reaches the air, meaning it bends away from the normal and into our eyes. However, as we know, the brain always interprets light to be moving in a straight line. So we imagine the lights have always been travelling in a straight line when it was in the water and to have not refracted. So we see the fish be further back and slightly higher up than it is really, which is one of the reasons why trying to fish or trying to spear a fish with a spear is so difficult. So using what we now know about reflection, refraction, and how our brains interpret light, how would you go about making an invisibility cloak to make something invisible? What would this cloak have to do to make an object invisible? Well, current research suggests that invisibility cloaks would work a little bit like this. Light enters from one direction and hits the invisibility cloak. The invisibility cloak then refracts the light around the object it's cloaking, until it then exits back out at the same angle at which it was coming in the first place. This means that when light reaches our eyes, and our brains interpret that light to have always been travelling in that straight line direction, it looks as if that object was never there at all. So is it possible to make this sort of cloak that could refract light around an object within it and back out at the same angle it came in? Well, yes and also no. Scientists have found that they've had to make special materials called metamaterials, which literally just means man-made materials or materials that don't occur naturally. These materials have a special property, having a negative refractive index. Think about how we saw earlier, that light would bend away from the normal when it sped up, or towards the normal if it slowed down. An object with a negative refractive index would have light bending the entire other side of the normal. Using these metamaterials with these negative refractive indices, scientists have been able to construct a small invisibility cloak, which could refract microwaves, which are waves with a larger wavelength than the visible lights to which we're used to see, around a very small 2D object of only a few centimetres in diameter. So in some instances, yes, we were able to make an invisibility cloak, which could cloak a small object to microwaves. But could we create something like we see in Harry Potter? No, we couldn't. Given the complexity of the structure of this invisibility cloak using these metamaterials, making an invisibility cloak like this for a large 3D object such as a person simply isn't feasible. So if so-called true invisibility is out the window, what about the sort of cloaking that you see on James Bond's car or on ships in Star Trek? This is actually much more feasible, and something to this effect has been achieved by a Canadian company, using a material which they've called quantum stealth because, of course, it's not real science until you put quantum in the name. They've developed a material which is a thin sheet of plastic, which has many cylindrical tubes on one side of it, which is called a lenticular lens. But really, all this material is the same material that's used in those holographic images, where when you bend the image around and it seems to shift around. How this works is that light from a person behind this, as it goes into the lens, is scattered in all directions, so that a viewer in front of it receives very little light from someone behind the lens, meaning that they're very hard to see. Although this distorts the background and therefore isn't true invisibility, it makes something behind it much harder to see, or cloaked. So there you have it, the truths and falsities of invisibility as depicted in pop culture. Whilst we can't recreate a true invisibility cloak for something the size of a person or in 3 dimensions, we can achieve cloaking for these sorts of objects using materials such as lenticular lenses. So if you have any questions at all guys, please feel free to leave something in the comments, I'll get back to you as soon as I can. But otherwise, thank you for watching.